Alright, today we're going to pull back the curtain on one of the most powerful tools in all of quantum computing. I'm talking about the engine behind some of the most legendary algorithms out there. It's a tool that can spot patterns that are totally invisible to our regular computers, and believe it or not, it has a surprising link to the music you listen to every single day. So let's dive into the Quantum Fourier Transform. Think about it. What could your Spotify playlist possibly have in common with the algorithms powerful enough to crack today's encryption? That sounds crazy, right? Well, the answer is this absolutely brilliant mathematical idea that jumped from our classical world, the world of sound waves and signals, right into the bizarre and wonderful quantum realm. And to really get a grip on its quantum power, we've got to go back. We need to start with classical roots, a world full of signals, waves, and totally revolutionary way of looking at them. So let's meet the man himself, Joseph Fourier. Back in the early 1800s, he had this incredible insight. He realized that basically any complex signal, I don't care how messy or jagged it looks, can be broken down and described as just a combination of simple, pure, and smooth waves. It's like taking a complex chord and figuring out all the individual notes that make it up. And that discovery, the Fourier transform, is everywhere. It's the secret sauce behind how your MP3 works. It finds the most important sound frequencies and tosses the rest to save space. That's how JPEGs compress your photos. It is quite literally the hidden mathematical language of our entire digital world. And this image right here, it just nails the core idea. The transform takes a signal that is all jumbled up over time. That's the new wave on the left. It kind of sorts it. It breaks it down into its fundamental ingredients, its core frequencies, which you can see on the right. It's a total shift in perspective. We stop asking, when did this happen, and start asking, what are the repeating patterns here? So that's the classical idea. Super powerful. But how in the world do we translate that into the quantum realm? Like many other things in quantum, we start very, very small. We start with the absolute simplest quantum system there is. And instead of a big, complicated system, we're going to zoom in on a single qubit. And it turns out the key that unlocks this whole thing, the quantum Fourier transform, or QFT for short, is a gate you probably already know. It's one of the more fundamental gates of all, the Hadamard gate. It's famous for one job, and it does it perfectly. It creates a perfect 50-50 superposition. You feed it a qubit that's definitely a 0, and it comes out a qubit that's equal mix of both 0 and 1. It really is the ultimate quantum coin flip. Get ready, because this is the final aha moment. Just look at this. On the left, that's the math, the matrix for the Hadamard gate. And on the right, that's the matrix for the simplest possible Fourier transform you can do on a simple two-level system. And they're not just kind of similar, they're identical. They're the exact same thing. So let that sink in. The secret is out. The Hadamard gate. The thing we use all the time to create superposition. It isn't just like a Fourier transform. It's the quantum Fourier transform for a single qubit. This is our ground floor, our foundational building block. But so what? Why is that such a big deal? Well, because the Hadamard gives us a key to unlock information that's normally hidden away in the qubit's phase. You could think of a phase as this hidden rotational angle on the qubit that you can't see with a normal measurement. If you just measure a qubit in superposition, you get a 50-50 shot at 0 or 1. It's random. But if you apply another Hadamard before you measure, suddenly the outcome isn't random anymore. It depends entirely on that hidden phase. It makes the invisible visible. So we've totally nailed the single qubit case. Simple enough. Now it's time to level up. Let's see what happens when we scale this into a system with many qubits and look at a full-blown math. This equation looks a little intimidating, but I promise the core idea is exactly the same as the Hadamard, it's just bigger. All it's doing is taking one input state, which we call x, and smearing it out into an equal superposition of every single possible state. But the really, really important part is that term with the e in it. That's the magical ingredient. That's what carefully assigns a very specific and unique phase, a little rotation to every single state in the superposition. That's how it encodes all that juicy frequency information. And that E term, the spooky part, it's really not that bad. All it is a super clever mathematical way of describing points that are spaced perfectly evenly around a circle, just like you see here. They have a fancy name, roots of unity, but you can just think of them as a ticks on a quantum clock. And it's this precise, perfectly repeating structure that gives the QFT its superpower, the ability to sniff out periodic patterns. So we've got this really elegant question on the board. That's great. But how do you actually build it? How do you tell a quantum computer, hey, do that? Well, the answer, as always, is a quantum circuit. And this is where things get really cool. Because that big, complicated looking equation, it can be built perfectly using just two kinds of really simple gates. The first one is our old friend, the Hadamard gate. And the second one is something called a controlled rotation gate. The way you build the circuit is this beautiful, almost dance-like repeating pattern. Here's the recipe. Step 1, you grab a qubit and hit it with the Hadamard gate. That puts it into superposition. Step 2, you do a series of controlled rotations, and these are super clever. They link the qubit's phase to the state of every other qubit, and then you just repeat. You do that for every single qubit in your system, and piece by piece, the full quantum Fourier transform takes shape. And voila, here it is, the final product. This is the complete circuit diagram for the QFT, and you can totally see that pattern we just talked about. Each horizontal line representing a qubit starts with H for Hadamard, and it's followed by the cascade of controlled rotation gates, the RK gates, that connect it all to other qubits. It's just an incredibly elegant and efficient piece of engineering. So why do we go through all this trouble? What's the big payoff? It comes down to one word: speed. An insane, mind-boggling speed up. Look at the best classical version of this, the fast Fourier transform. It takes about n log n steps. The QFT takes about n squared steps. Now that might not sound that different until you remember the crucial part. N, the number of states, is 2 to the power of n. So let's say you have just 20 qubits. Classically, you're looking at over 20 million operations. Quantumly, you're looking at 400. That's not just faster, that's a fundamentally different way of computing. It's a true exponential speedup. So we've built this incredibly fast, ridiculously powerful tool. We've got our quantum hammer. But what do we hit it with? What's the killer app for the QFT? The answer is simple. The Quantum Fourier Transform has one main superpower. It's the ultimate pattern finder. It's designed to sniff out hidden repeating patterns, what we call periodicities, that are buried deep inside quantum data. So here's the game plan. Imagine you have some quantum state, but hidden inside its amplitudes is a secret repeating pattern. If you just measure it directly, all you get is random noise. It's useless. But if you first pass that state to the QFT, it acts like a magical lens. It takes all that spread out probability and focuses it like a laser beam right onto the states that match the hidden pattern. So what you basically measure after the transform, you almost guarantee to get a result that basically shouts the secret pattern back at you. This quote here really just nails the mathematical payoff. It's a bit dense, but what it's saying is this: once you run a QFT on a state that has a hidden period, let's call it R, the measurement you get, let's call it J, isn't random. The math guarantees a special relationship between them. From that relationship, a little bit of classical math can easily work backwards, figure out R, the hidden period you were looking for all along. And that right there, that incredible ability to find the hidden period of a function, that's the beating heart of Shor's algorithm. The algorithm that can factor huge numbers and, yes, break much of the encryption that protects our digital world today. More about that on a separate video. I should have a link down. The QFT turns a classically impossible problem into a quantumly solvable one. And that just leaves us with this one massive question. If it can find this pattern, what other profound hidden patterns in physics, in chemistry, in financial markets are just sitting there waiting for the quantum Fourier transform to uncover them? Thank you for tuning into another episode of Quantlock. Goodbye.